All right, let's take a look at a level 2 cliff scenario and how you can find out multiple things about the motion of an object from a cliff using Desmos. So if you look at the learning target, learning how to analyze the motion of an object in free fall, and the success criteria, you should be able to create an equation and use Desmos to analyze the motion of an object in free fall. All right, so if we take this scenario, the ball is thrown straight up at 20 meters per second from the top of a 75-meter high cliff. So it's going to go up, reach its peak, and then go all the way down to the water below. So what can Desmos help you figure out about this cliff scenario? Well, you can really figure out a few things. You can figure out how long it's going to take the ball to reach its peak, what the maximum height of the ball will be at the peak, and how much time it's going to take for the ball to reach the water below. So we're going to analyze the ball's whole trip, and let's see what we're dealing with in terms of the information we're given and what we're trying to find. So the initial velocity, ball's thrown upward at 20 meters per second, and gravity is pulling it down at 9.8 meters per second, or negative 9.8 meters per second squared. And displacement, remember, displacement is where the ball ends up compared to where it started. It's going to end up 75 meters below where it started at the top of the cliff, so it's negative 75 meters. And we're trying to find time. So we're only directly setting up to analyze the ball's whole trip to get how much time it takes to get to the water. But you're going to see how soon Desmos will actually answer all those questions on the previous slide, not just the one we're directly setting up for. So if you look at this combination of variables, that's going to set up for using the quadratic, d equals VIT plus 1/2 AT squared. So substituting our values in, and then we can clean this up a little bit. 1/2 of negative 9.8 is negative 4.9. And if you look here with this equation, the way it's set up right now, displacement is expressed in terms of the time that the ball is in the air. So the time the ball is in the air is going to be the independent variable, and the ball's displacement depends on it, so that's going to be the dependent variable. So when we make a graph of this equation in a little bit, the independent variable t time, that'll be on the x-axis, and d displacement will be on the y-axis. So basically we're going to end up graphing, making a position time graph for this ball's motion in the air. So we'll see that soon enough. So we're going to put this equation that we've created in standard format of ax squared plus bx plus c equals 0, so that we can ultimately solve this equation for time. So all we did is add 75 to both sides to make the equation equal 0. And this right here is what you're going to graph in Desmos. So let's pull up Desmos for that. Graphing calculator. This out of the way here. So now we're going to put our equation in. So negative 4.9. And they don't have t, but just use the generic x. And then here's the exponent for squared. And watch, as soon as we add this, it'll take this line and convert it to a parabola. So negative 4.9 x squared plus 20x plus 75. We're just graphing that expression. Now from here, if we zoom out, we now have a parabola showing the motion of this ball throughout its flight. And so there's some critical points that you can get off of this graph here. So first things first, you'll see, again, we talked about, if you go back to the equation, d equals VIT plus 1/2 AT squared, the ball's displacement is expressed as a function of the time that it's in the air. So times the independent variable, that's the x-axis, and displacement's the dependent variable, that's the y-axis. So this is basically a position time graph for the ball's motion. So right here, the y-intercept at a time of 0 seconds. So at the beginning of the problem, the ball is 75 meters high. It's at the top of the cliff. And then if you look at the vertex, identify the x and y coordinates of the vertex. At about 2.04 seconds, the ball reaches its maximum height, and that height is the y coordinate, which is the ball's position, of 95.4 meters. And now we go all the way to the bottom, this x-intercept here. Here's the time to hit the water, 6.453 seconds. So again, just to sum up, you have this equation here, and then we're going to have to rearrange it to put it in the standard form of x squared plus bx plus c equals 0. And once you've done that, then you can take this expression on the left, graph that in Desmos, as we just did. And then again, you can see it gives you these critical points here, where you've got the starting height at time 0, and then the time for the ball to reach its peak at 2.04 seconds, the maximum height at the peak being the 95.4 meters, and then time for the ball to reach the water below, 6.453 seconds. All right, hopefully this helps.